For molecular compounds, there are two different types of formulas. And so these are for what we've been calling covalent compounds. And we have been doing the molecular formulas. These are the correct formulas. They actually show what is in one molecule, as a formula should for a covalent compound. However, we do talk about empirical formulas sometimes. And basically this is a formula that has been reduced. Now, it's normal to do that for an ionic compound. They're always reduced. Normally we don't for molecular, because we're trying to show what is in one group. But this empirical formula has a purpose sometimes, and sometimes we will actually be doing some calculations to determine that. So it does kind of have a purpose, even though it's not really showing everything there. So just to distinguish these two types, the molecular formula, and this is if I ask you to write a formula, this is the kind you do. But if we ask for an empirical formula, it's just the reduced version. So the reduced version of this. A little bit more about bonds, and we've been talking about this, but when we say an ionic compound, that means it has ionic bonds. The bond is what holds the atoms, or in this case ions, together. And an ionic bond is between a metal and nonmetal. And of course, it's the ion version of those. A covalent bond, instead of a transfer of electrons that gives you ions, a covalent bond has sharing of electrons. And for these, these are for non-metal compounds that we have sharing. So all the time we've been saying covalent compound, non-metal compound, we have sharing of electrons. Ionic compound, we have transfer, which leads to ions. Another kind of bond is a metallic bond. And this is if you have metal atoms only. When you put two metals together, they don't really form a compound. It's considered a kind of mixture, like a metal alloy. But there is a kind of bond that when you put a bunch of metal ions together, they basically will be all sharing electrons. Electrons will just be shared throughout the whole thing, which is why metals conduct electricity. Another thing about atoms is we have what's called periodic law, and this has a lot to do with predicting the charges of ions, like we did. In other words, we use the periodic table to determine what charge of ion sulfur would form, and it would be in the -2 column. This is because of periodic law. Also, because of periodic law, we have groups and families where a column has similar properties, and these, of course, follow with the charges we said. All of these form +1 ions. You need to know these four family names. These are alkali metals. Need a space in there. And these are alkaline earth metals. And then over here, these are the halogens. And these are the noble gases. I put group 1 here and group 2 because those are very common names for those two. They'll be called those probably group 1 and group 2 probably more often. The other group numbers we don't use quite so much, just those two. Also on the periodic table along this zigzag, which that zigzag is right here, there are elements in orange that are metalloids. They have kind of in-between properties. Remember, metals, their main property is they tend to give up electrons, and the nonmetals up here tend to hold on to their electrons. Here's this business of metallic bonding. If you have a bunch of metal atoms, they basically just share electrons. Electrons are flowing freely from one to another, and this has to do with having easily transferred electrons and also a space for them to go. Another kind of compound we've been talking about ionic and covalent as though they're the only two. There are actually also acids, which are kind of different. They are nonmetals, so they look covalent, but when you put them in water, they ionize, so they act ionic. So acids and bases, we'll be talking about those a little later. And then organic versus inorganic. Organic molecules are carbon-based. And we didn't talk about those in this lesson, this unit, because it's a whole nother category. So I'll just show you a little bit. These are mostly covalent bonds, and so they are sharing of electrons. Here's some definitions you need to know. When you are sharing, two atoms are sharing a pair of electrons, that's 2 electrons, that's called a single bond. 2 pairs or 4 electrons shared, that's a double bond. And inorganic refers to all other compounds. So organic compounds are carbon-based, and everything else that's not carbon-based is inorganic. Let's just look at some organic compounds. The reason that organic compounds kind of have their own system is that when you have a formula, that formula is ambiguous because for those atoms, there may be more than one way that you could connect them. And if they're connected in different ways, they're different compounds. So a lot of times for organic compounds, we have to draw structures. And so this structure right here, this is a full structural formula. A structural formula rather than just showing a molecular formula like this. And a lot of times we just call that a structure. On this structure, so here is a simplified version of the structure. A lot of times we leave the hydrogens off because in organic chemistry there are a lot of hydrogens, and so we kind of know they're there by default. But notice that these dashes tell you what kind of bonds. This is a single bond, a double bond. Okay. And then sometimes we draw the structures like this. This is a line structure. It's a real shortcut, and it's just that it's understood that there's carbons at every bend and every end there. So another way to show it. Again, well, these are this compound, but there's more than one way these could connect, and each way would give you a different compound. A kind of organic chemistry is one kind is a polymer. A polymer is when you have many smaller units connected in a chain. And so this compound here, basically it can do a reaction so that it's connected. It loses its double bond, but these are units of that are connected together in a long chain. And you know, when you think of polymers, think of plastics. But anyway, so this is ethylene, so we call this polyethylene. Here's that word again, empirical formula. Empirical formula was the reduced one, and maybe now you see why it's reduced, because this compound actually would go on in either direction for thousands of units. So it wouldn't make sense to, like say carbon 1000, hydrogen 1000 or whatever. We might look at the ratio, and you can tell the ratio here of carbon to hydrogen is that for every carbon you have 2 hydrogens. So this is a case where the empirical formula has a good purpose. Okay, and one thing I want you to know about polymers is that when you have these really big molecules, the properties of the polymer depends on how the molecules are connected or what their shape is. So these are all polyethylene. In this one, and we're not showing the full chain, they're much longer than this, but in this one the chains are kind of aligned, and this would be a stronger fiber than if they were all squiggly. Now this one has cross-linking, so they basically do a reaction to connect the different chains. This makes it a lot stronger to do that. This one has branches, so they don't all line up neatly. They kind of form, and so this makes a much more flexible type